I'm going to start with this piece of the night sky, and some of you might already recognize the constellation in it. But for the sake of people like me who can't, I'll put in the lines. It's part of Ursa Major, the Big Dipper, and next to the handle I've got a circle and an arrow. The object that's circled is the Pinwheel Galaxy, which is about 20 million light years away and about 4 times the size of ours. And as much as I love the Pinwheel Galaxy, it's not the focus of this video. The arrow is pointed at another galaxy entirely, one that's around 50 times as far away, 1 billion light years. It was first observed in 2008, but it doesn't have a name yet, only a designation, which I'll put right here. Now, to keep myself sane, I'm not going to read off all that. I'm just going to call it J13. This is the Swift Space Observatory. It was launched into orbit in November of 2004, and its original mission was to observe and record the data from gamma ray bursts. But since it has multiple detectors on it, it's been used to map the night sky and observe targets of opportunity. On April 29, 2020, it detected a transient event, a flash of light in the visible and UV spectra that was coming from J13. When the light was analyzed, researchers found a jump in the Helium II line on the blue part of the visible spectrum. Now, to give you an idea of what that looks like, I'm using this figure. The image shows the brightness of each part of the spectrum, so where the line goes up, that part of the spectrum is brighter. The elements causing the emissions are labeled. The bottom line is the original spectrum from 2000, and the top line is data from 2015. You can see in the 2015 data that there's a jump in this section, which is noted Helium 2. It turns out this pop in the spectrum is strongly associated with tidal disruption events. A tidal disruption event is the process where a black hole captures a star, tears it apart, and eventually consumes it. When researchers realized this was happening, a request was sent to use the NICER telescope on the International Space Station to monitor the transient event. NICER collected data several times a day, including the X-ray spectrum. Using that data, these researchers were able to make an estimate of the rate of spin of the supermassive black hole at J13's center. And it's the first time that's ever been done. I want to talk about the findings and how the researchers came to them. Along the way, we're going to discuss tidal disruption events and accretion disks. We'll look at the data the researchers used, and we'll also get into Lense-Thirring Precession, radiation pressure instability, and other possible explanations for the data. We've got a lot of badass stuff to cover here, and we're just getting started. So let's get into it. I'm Cameron, and this is my channel. Welcome to the Sexy Universe.
All the stars in the sky, all the lights on the highway, oh, they keep us coming alive.
In a tidal disruption event, a star enters the gravity well of a black hole and accelerates toward it at breakneck speed. Even though a star's gravity is strong, the gravitational forces and acceleration around the black hole are much stronger. The shape of the star warps until it's torn apart entirely. Some of the gas achieves escape velocity and is thrown clear, while the rest forms an accretion disk in orbit around the black hole. An important thing to remember about accretion disks is that the gravity is so strong that the particles have to move at relativistic speeds to maintain orbit. Relativistic speeds are defined as being between 14% and 95% of the speed of light. At those velocities, there's enough friction between the particles in the disk to superheat the entire thing, and the whole disk lights up, brighter than any star ever could. This image shows the transient light from J13 in the UV and visible spectrums. As you can see, the brightness starts out high and then slowly fades over several weeks. And this is typical of tidal disruption events. The light fades as the gas in the accretion disk falls into the black hole. As material falls toward the event horizon, Coriolis effects speed some of it up even faster and spin it toward the poles. This heats the gas even more, creating X-ray emissions and firing some of the gas back into space. It creates an emission jet, like this one that comes out of Galaxy M87. I'm using this video from NASA as an illustration, and it isn't a black hole. It's actually an animation of Pulsar J1023. A neutron star has caught another star in its orbit, and it's pulling material from it. The stellar material forms an accretion disk with X-ray jets at the poles, and the same thing is happening at the supermassive black hole at J13. But this is where the mystery deepens. When we look at the X-ray data, we can see that instead of having a steady emission, it starts out low, jumps up, and then falls again. And all this happens at regular intervals of about 15 days. So what's causing it? The researchers came up with 5 different possibilities. The first was multiple tidal disruption events. Basically, this means the star is caught in the black hole's orbit, but not falling into it. So just like the video of the pulsar shows, the black hole is taking the star apart one bite at a time. But if that was happening, the UV and visible spectra would be jumping every 15 days along with the X-ray spectrum. And we know they're not doing that. So this hypothesis was rejected. The second possibility was that variability was being caused by stream collisions. This means that streams of matter in the accretion disk intersect and crash into each other, and this causes some of the material to fall out of orbit and drop quickly toward the event horizon. But if this was the case, the pattern of jumps in the X-ray spectrum would be random, not occurring at regular intervals. So this hypothesis was also rejected. The third was radiation pressure instability. This happens if the accretion disk heats up unevenly. Radiation and light from hotter parts of the disk push on the cooler parts of the disk and alter their trajectories. The researchers found that this was only possible in one specific case, which I'll describe later. So the hypothesis wasn't rejected, but it wasn't found to be the most likely. The fourth possibility was Lense-Thirring Precession. Going back to the pulsar video, the accretion disk is aligned with the equator of the pulsar, so its X-ray jets are aligned with the north and south poles. But what if, instead of being aligned, the accretion disk and the black hole's equator were a little off kilter? Then the X-ray jets would also be misaligned from the poles of the black hole. And as the black hole spun, it would cause the orientation of the disk and the jets to wobble. Then we would expect the X-ray emissions to drop when the jet pointed away from us, and then jump back up when it pointed at us again. This was found to be the most likely explanation. Now there was also a fifth possibility, and it was that instead of there being a single disk, there could be multiple rings. But even as the rings were consumed, you would still need Lense-Thirring Precession to take place in order to explain the 15-day interval. This hypothesis couldn't be rejected, but it might be in the future. If there are multiple rings of material, we should see a drop in all emissions with a restart somewhere down the line. And if that restart is picked up in the future, this will become the most likely explanation. But for now, it just can't be proven either way. In order to solve the riddle, the mass of J13's central black hole had to be determined. To do that, researchers looked at the velocity dispersion around the galactic bulge. This is done by taking a sampling of visible stars, adding up their velocities, and dividing by the sample size to get the average velocity. Then the statistical variation is calculated from the average, and it's called sigma. Then the mass of the black hole could be calculated from this equation. Using that method, the black hole's mass was found to be somewhere between 630,000 and 10 million solar masses. And while that sounds like a pretty big range, it's actually not that bad, when you consider the distance and that J13 wasn't looked at very much until recently. Now back to the Lense-Thirring Precession hypothesis. The rate of precession depends on several factors. Those include the mass, radius, and trajectory of the incoming star, the inner and outer radii of the accretion disk, and the mass and spin rate of the black hole. By taking the precession equation and rearranging it to solve for the spin of the black hole, the researchers came up with this equation here. Some of the parameters, such as the star's mass and dimensions of the accretion disk, had to be estimated. But the mass of the black hole and the rate of precession were known. So based on a few assumptions, a range of possible spin rates for the black hole were found. These charts show the possible spin parameter values for different black hole masses. This first one examines the case of the heaviest possibility for the black hole, 10 million solar masses, represents the observed precession period of 15 days. The red dotted lines show the possible values for the spin parameter, about 0.05. And if I've translated their equation correctly, this would correspond to a spin period of 1.2 hours. This would mean particles attached to the inner boundary of the event horizon would be traveling at about 26,700 miles per second, or about 14% of the speed of light. This is the lower limit for relativistic speeds. Looking at the other two cases of a much less massive black hole, you can see the possible spin parameter values have a wider range. If more thorough data were available for the estimated parameters, these ranges could probably be lower. This is the first time the spin of a black hole has ever been calculated, and I'm pretty impressed with the work. Now before I end the video, I want to go back and touch on the radiation pressure instability hypothesis. The only case the researchers found where the hypothesis was useful was if the supermassive black hole's mass was 5 million suns. But since the measured mass has a wide range of possible values, this is the less likely hypothesis, but it's still possible. And what it highlights to me is the importance of remembering that when we study nature, we have to keep our minds open to the uncountable possibilities in the universe around us. I believe the ideal life is a non-stop process of learning and growing. Thanks for learning and growing with me. I want to hear what you think, so please put any thoughts you have or information you'd like to share in the comments section below. And hit the like and subscribe buttons on your way out. Stay on your game, and I'll see you next time on The Sexy Universe.